In this example, we have a particle P which is able to slide along a smooth rod. And this rod is rotating about a vertical axis. And what we know is that when the arm is rotating with a rate of 20 radians per second, and r is equal to 3 inches, the P is stationary with respect to the rod. So it has an initial velocity, but it's only due to the rotation. Then once that thing is released, then P will start to move out on the bar. And what we want to do is find the angular speed of the arm once P is moved outward to a position of 24 inches, where it starts out at r equal to 3. Okay, so what I'm going to do is draw a free body diagram of the particle and the rod. One thing it says in there that the rod has negligible mass. So the only thing having mass in this case is the particle P. Okay, so if I look at that system as a whole, we have the potential here for some reaction forces of OX and OY here. And that's it. That's the only forces that are acting that we can see in this plane. So the observation to be made here, and we're going to use the angular impulse momentum equation. And the reason for choosing that approach is that we make the observation that although there may be forces acting there at O, they act at O, and therefore there's no moment that is created at O. So that says for our system, angular momentum at time 2 is equal to what it was at the beginning. In other words, as this particle P moves out, it's changing in velocity, but it's changing in velocity in a way that h is a constant. And the reason we know that, again, is that the only thing that we have are the forces OX and OY, and they cannot create a moment about O. I'm going to use a polar description here, ER and E theta, like this. And so whenever I write down my angular momentum at 1, HO1, that's always R cross MV. And so R in this case is just this radial distance R1 in the direction ER, crossed with the initial velocity. Well, the particle P is not moving relative to the arm, so it simply has a theta component, and that's going to be R1 omega 1 in E theta. ER crossed E theta is a K, so I have M R1 squared omega 1K at time 2. We write down the same expression, except this is evaluated at time 2. So it's still R cross MV. The R vector is just the new radial distance ER. Now P it says moves out, so it's going to have a radial component R dot for velocity, as well as the R2 omega 2. Like that. An important thing to observe here is that it's moving outward, but that doesn't change a thing, because ER crossed ER is a 0. Anytime you cross a vector with itself, it's a 0. So although R dot's there, it doesn't really come into play. So we have M R2 squared omega 2K. And since we showed from our FBD that H is a constant, we have M R1 squared omega 1 is equal to M R2 squared omega 2. So from this we can find the rotation rate of that arm, we cancel out the m's, is equal to ratio of R1 to R2 squared omega 1. R1 was 3 inches if I recall right. R2 is 24. And omega 1, sorry I have to keep coming back here, is 20. So this is the rotation rate at time 2. Let's go back to see how we got that. It all began by looking at the FBD of the particle in the arm. The arm has no mass. So when we write down angular momentum, it's just of the particle. And the important observation here is that since the only forces acting on this that we can see are OX and OY pointing through point O, they're there, but they don't make any contribution to a moment about O, and that's how we got this. H is a constant. It was a matter of evaluating H initially, R cross MV, and evaluating H for position 2. Although P is moving outward with a component of R2 dot in addition to the R omega, that part does not come into play. That's always going to be the case. The radial component of velocity will not appear in H, which is good for us because we were able to now get a single equation for omega 2 without having to worry about R2 dot.